Hello everyone, welcome to NPTEL online course on electric vehicles. So let us start the next topic under vehicle dynamics, which is the simulation of dynamic equation when the vehicle is driven by constant FTE. So in our previous interaction, we have derived many dynamic equations for the case where the vehicle is driven by a constant tractive effort force. So we can say that the motor is driven by a constant torque output. So in this case, we have seen the equation of dV by dt in terms of the motor torque and different resistive forces. So we have rewritten the equation in terms of constant K1 and K2. So K1 is constant because these terms are constant, and K2 is constant because all these terms are constant in addition to the motoring torque. So K1 and K2 have these values, and we have solved this equation and rewritten them in terms of terminal velocity and K1. So this was the equation we have derived, where the terminal velocity is root over K2 by K1. So since the velocity has graph, similar to this, and if we assume Vt to be constant here, and so we were interested to find the time taken to reach the vehicle for a speed which is equal to 0.98 Vt. So we have got expression equal to Tf equal to 2.3 divided by K1 Vt. Similarly, if we want to calculate the distance travelled in time Tf, it can be found out using this equation. So power with respect to time has very similar graph as the velocity, because the FTE is constant and PT as a function of time is a product of FTE into Vt. So P also will have a similar graph as velocity. This is P of t, this is terminal velocity of power. So the terminal velocity will be again FTV into root of K2 by K1. So in our previous interaction, we have also seen that the calculation of average power due to tractive effort is a function of Pt terminal velocity divided by Tf 1 by root of K1 by K2 into log of cos h root of K1 K2 Tf. So the calculation of P average is very handy, because it will help us to know the energy which is required to drive the vehicle up to terminal velocity, or the velocity which is equal to Vf. So Vf is 0.98 Vt we have assumed. The energy required can be calculated just as a product of the time elapsed and the average tractive effort power. So let us take an example and calculate all these variables. So let us example of a battery electric vehicle which is given a constant input motor torque. So, let us assume that the gear ratio is 10:1. The radius of the wheel is 0.2 meters. The rolling resistant coefficient, which is mu RR, is 0.01. The drag coefficient due to aerodynamic force is 0.26. The frontal area is 2.2 meter square. Let us assume that the mass of the vehicle is 1200 kgs. So, we also have to calculate the equivalent mass due to inertia of the motor, which is Jm into G by R square into 1 by efficiency of the gear. So, if this Jm is not known, the equivalent mass with respect to this term can be assumed to be 5% of the mass of the vehicle. So, let us assume that, and it is quite reasonable approximation. So, m1, let us tell us 5% of m1. The efficiency of the gear, let us take as 0.9. The air density 1.25 kg meter cube. Let us take the maximum torque of the motor, which is equal to 14 Newton meter. So, this is the torque which is given as input to this system. To start with, let us assume that the slope angle is 0 degree and the wind velocity is also 0. So, with the parameters of the given vehicle, we can estimate the value of tractive effort force as G by R into T max into efficiency of the gear. So, it will come out to be 1800 Newton. So, it is basically 10 by 0.2 into 40 into 0.9. Similarly, we can also calculate the force required for rolling resistance force, which is mu RR into mg cos of theta. So, cos theta is 1, therefore, this is coming to be 117.72 Newton. The force due to gradient will be 0 because the theta what we have assumed is 0 degrees. Let us also calculate the constant term of the aerodynamic force, which is 1 by 2 rho AR into CD. So, this will be 0.3575. It will be used for calculation of K1 and K2. So, constant K1 is FTE minus FRR minus FG by m plus m1. So, m1 is 0.05 m. So, if you substitute all these values here, we will get a constant K1 of 2.83 into 10 raised to minus 4 meter per second square. Similarly, the constant K2 can be evaluated as the constant we have calculated here divided by m1 plus m, which is 1.33, the unit is 1 by meters. So, since we have all these values available with us, we can now calculate the rest of the parameters. So, the terminal velocity is a square root of k2 minus k1, and it can be calculated as 65.89 meter per second. So, which becomes 246.95 kilometer per hour. So, this vehicle can go to the maximum speed of 246.95 kilometer per hour for a constant input torque from the machine equal to 14 Newton meters. If you want to calculate most of the variables for the value of velocity which is 0.9 times of this terminal velocity, which is equal to 242 kilometer per hour. So, the time required to reach this velocity can be calculated by using this formula. So, 2.3 divided by k1 into v terminal. So, this is 118.17 seconds. So, it takes almost 2 minutes to reach this velocity close to 0.98 v terminal velocity. So, the distance the vehicle travelled in time Tf can be calculated using this formula we have seen earlier, and if we divide by 1000 we will get the value in kilometers. So, the distance travelled is 5.7 kilometers. Similar to terminal velocity, we can also calculate the power. The maximum power this system will take is V terminal into FTE divided by 1000. So, we will get the power in kilowatt. So, it is 123.47 kilowatt. The power that is required to operate the vehicle at 0.98 of V terminal, which is VTF, will be equal to 0.98 of this value. So, it is 121 kilowatt. So, as we discussed, it will be very handy to calculate the average value of power that is required to bring the vehicle to a velocity which is 0.98 into Vt. So, if we substitute this formula here and give suitable values of Tf and V terminal K1 etc., this value comes it to be 86.80 kilowatt. So, this value of P average will be used in calculation of the energy required to bring the vehicle to time Tf or velocity equal to 0.98 Vt will be equal to P average into the time elapsed, which is Tf, and we have to divide by 3600 to bring it into our value. So, it will be 3.165 kilowatt hour. So, the equivalent value of joule can be calculated using this formula as well. So, we are able to calculate the values of most of these variables using simple formulas which we have derived. Now, let us try to plot this using Simulink program and see the actual variation of different variables with respect to time. For the same example, if you want to plot the velocity with respect to time, it will come like this. So, the velocity will start from 0 and 0 seconds, and it will go all the way and become steady state. So, the value will Vt after some point of time. So, we have seen this value of Vt equal to basically 246.95 kilometer per hour. So, the time required to reach 98% of this speed, which is 242, which will come in a time somewhere here. So, this is Tf equal to 118.17 seconds. So, here the value of is 242 kilometer per hour. So, this is Vf, this is Vt, and this is Tf. So, this plot shows us the variation of the velocity with respect to time. Similarly, if we want to plot distance travelled as a function of time, we can also do that using Simulink programs. So, as the velocity increases, the distance travelled also increases. So, in around 118, so Tf equal to 118.17 second, we will reach a speed or speed of 242 kilometer per hour, and the distance equal to, so this is SF equal to basically 5.698 kilometer. So, this also values is coming as per the calculation we have done. So, distance will keep on increasing because the speed has become constant, and distance is speed into time. So, it will keep on increasing because the speed has not become 0 and it is becoming constant. Similarly, we have the plot of instantaneous power, which is PTE as a function of time. So, we can see that the plot of instantaneous power is very similar to the velocity graph. So, it increases from 0 and become constant at value equal to P terminal. So, P terminal in our case was basically 123.47 kilowatt. So, at Tf, the P required at Tf was 121 kilowatt. So, if we try to find the average value, which we have done, the average value is this, and it will be equal to P average was 86.8 kilowatt. So, it will also be an interesting idea to see all these graphs together in a single sheet. So, the bold graph is, so this graph is the what we have seen in previous 3 graphs. So, let us take an example where the same vehicle is traveling on a constant slope of 5 degrees. So, in our previous case we have assumed the value of slope as 0, but if there is a condition that the vehicle is driving on a slope of constant 5 degrees, then what will be the graphs and the values of voltage, distance and power. So, the second case of slope of 5 degrees is plotted in dotted line. So, if we see the Vt1, the terminal velocity for case 1 is 246.95, we have seen. The terminal velocity for second case is 154.3 meter per second. So, it means that so the terminal velocity is reduced in this case. The time to reach 98% of the terminal velocity will be 118 for the first case and almost 190 second for the case where the slope is 5 degrees. The distance travelled in this time is same, because distance is product of velocity into time. The average power that is required in the first case was 86.8 kilowatt, we have seen. In the second case, the average power required becomes low, which is 54.23 kilowatt. So, the average power has reduced. On the other hand, the time required to reach 98% of the terminal velocity has increased in the second case. So, because of this thing the energy required, which is product of P average into T f, remains constant for both the cases. Similarly, let us assume a case where the mass is reduced from 1200 kgs to 800 kgs. So, the graph pertaining to 800 kgs will be plotted in a dotted curve. So, there is no much difference between the two graphs. So, the acceleration is better in the case where the mass is lower. So, terminal velocity are very similar. So, in first case it was 246.95 and second case it was 249.81. But since the acceleration is faster in the second case, the time required to reach the 98% of terminal velocity is lower in the second case. So, it is reduced from 118 to 77.87. The distance travelled to reach 98% of the velocity will be 5.698 kilometer in the first case, and it was 3.79 kilometer in the second case. The average power is also similar, but there is interesting thing that the energy required to travel in the second case has reduced from 3.165 to 2.11, because the average power is similar, but the time required to reach 98% of the terminal velocity has drastically reduced in second case. So, the proportional reduction of energy can be seen. So, using this kind of simulations, we can check the vehicle performance for the constant input motor torque for different kind of change in variables and conditions. So, how do we check these conditions? So, we have to write a MATLAB program very similar to we have seen in the previous interaction for calculation of different resistive forces. So, we know the equation of velocity is dv by dt equal to minus k1 v square plus k2. So, this equation is a function of time, and we can do time step simulation, which is possible in MATLAB or C programming or any other, even Excel can be used to do this. So, we can write dv by dt as v n plus 1 minus v n divided by delta. So, if we substitute dv as difference of v l plus 1 minus v n and dt as delta n, we can get this equation. So, v n plus 1 is v n into delta t into product of this. So, this velocity also will become v of n, which is the current velocity. So, if we start from v n of 0 and keep substituting new values of v n plus 1 in the next sample for the values of k1, k2 and delta t, we will be able to plot these values with respect to time. So, similar to the previous case of the simulation file for resistive force calculation, we are again putting the simulation file that is used for the plot of velocity, distance and power here for reference. So, first we have to define parameters and values. So, g equal to 10, r equal to 0.2, mu r of 0.01, CD of 0.26, AR of 2.2, M of 1200 kgs, and M1 is basically M plus 0.05 M. So, we are together telling this as M1. So, this is the total mass. So, this is M plus the 5% of the total mass for the moment of inertia of the motor. Efficiency of gear, let us take as 0.9, rho 1.25. The maximum torque of the motor is 40 Newton meter, and the slope angle is 0 and the wind velocity is also 0. So, after defining all the parameters and their values, we can calculate the tractive force, rolling resistance force, gradient force, and the constant of aerodynamic force using the formulas. So, these are simple formulas we have seen. So, after the variables are defined and their values are given, in the next step we have to write program for initializing the arrays for storing the different values of velocity, distance and power at different time steps of, let us say, 0.1 second for simulation. So, first we have to define arrays for storing the values of velocity, distance and power. So, since we are having a TF equal to 118 seconds, let us take a total time for simulation of 150 seconds in a time step of 0.1 seconds. So, if we do so, we need 1500 values to be stored for each of these variables. So, first we have to define that, and dt is 0.1 seconds. Later we have to run a for loop where the new values of velocity, power and distance will be calculated on the current values of velocity and other variables. So, V n plus 1 is V of n plus d by dt of k2 minus k1 V n of square. Similarly, power is V current value into FTE. We know that velocity is distance by time. So, since we know that velocity is distance by time, we can write V n equal to d n plus 1 minus d of n by delta t. Therefore, the new value of distance can be calculated as the previous value of distance and the del t into the previous value of velocity. So, in this way we can write the time step based calculation of different variables. After this, so once the values of velocity, distance and power is available for 150 seconds in a time sample of 0.1 seconds, we can plot those with respect to time in respective plots. So, there is another thing which we have missed in the previous discussion, is that during motoring operation, the power flow happens from motor to the driving axle to the wheel using gears. So, equation of T motor is T motor equal to 1 by G 1 by efficiency G into T axle. So, the motor torque is greater than T axle torque because the power flow is happening from motor towards wheel. But in case of generation or braking operation, the power flow happens from wheel through gears to the motor, power converter and battery. So, motor will operate as generator and the power is absorbed from the wheels and given to the battery using power converter. So, the direction of torque has changed with respect to the angular velocities and also the power flow. But the equation of Tm with respect to Txl is now eta g by g. Why it is so? Because the input torque is Txl and the output torque is Tm. So, Txl has to be greater than Tm. So, this equation change has to be kept in mind. So, we know that the tractive effort, which is sum of all the forces, can be written in two ways. First is Ft equal to the addition of all forces plus accelerating forces. The second way is in terms of ABC constants. So, the force equation in terms of ABC has a term which is BV. So, it takes care of the forces with respect to velocity variation. So, this is important term because it captures no load spinning losses such as windage losses etc. of all the transmission system. So, if we calculate the graphs of velocity, distance and power, energy etc. based on this equation, it will be more accurate. So, that is all under simulation of dynamic equation with constant Ft. So, in our next interaction we will discuss the dynamic equations if the input tractive effort is a variable one. So, we will see the derivation of equation with variable Ft conditions. So, thank you for listening the lecture. Thank you.